Good morning, everyone. In today's lesson, we're going to be able to identify different chemicals by a photospec. So, what we're going to look at now is the different atomic spectra. So, all the atomic spectra is remember those different energy levels we just completed? Each one of those different energy levels, when it bounces from, say, an n equals 1 to an n equals 2 state, or an n equals 3 to an n equals 4, or an n equals 6 to an n equals 8, it's going to require energy to be poured into that atom. Now, when it goes from a higher energy level, like n equals 3 to n equals 2, what it's going to do is it's going to release a bunch of energy in the form of light. That light we're going to be able to harness and find out what its energy value is from its wavelength or its frequency. So you've done this in chemistry where you've looked through the spectroscope. And the spectroscope is going to give you the different wavelengths in nanometers. So what you can do is you could find out how much energy this little purple or violet line is going to be released from that atom. So there's two different types of spectrum. There's an emission spectrum and there's an absorption spectrum. They give you the same exact numbers, they just do it in a different manner. So with an emission spectrum, this is the one that we see in the spectroscope in chemistry. What you'll see is the different colors of lines, and if you notice, each one of the lines is basically going to be red, is going to be over in the 6 to 700 nanometer range, and anything in the lower wavelength range is going to be your violets, and then there's going to be obviously the spectrum of the rainbow in between. So you should be surprised if you see a red line over here. So you'll always see red lines over here towards the high end, and you'll always see violet lines towards the bottom end. The absorption spectra. So if you look on the bottom is the emission, on top is the absorption. So what they do here is they shoot basically the electromagnetic radiation through the different medium, and what happens is it then gets absorbed by the hydrogen. So instead of it releasing this violet line, what it's going to do is that hydrogen atom is going to absorb that violet line. So it does the same exact thing. If you notice, these things should line up. But what happens is they basically shoot the white light at the hydrogen atom, and what happens is the hydrogen atom absorbs those colors. So you see every part of the rainbow except the ones the hydrogen absorbs. So that's considered the absorption spectrum. Now, this is useful because since we can use the absorption or the emission spectra, we can identify what elements are in that type of compound. The next thing is the fundamental forces of nature. So we spoke about this a little briefly on the previous slideshow, but the strong force is responsible for any of those nuclear attractions. It is an immensely powerful force, and we're going to do all the relative strengths based on this strong force. So what happens is if we consider this the gold standard, the relative range here is very, very tiny. This is the reason why we only find it in the nucleus of our atoms. The range here is not large enough to reach out to the electrons, and it is not long enough to even go from atom to atom. It is extremely strong, and by breaking this is where we get all that energy potential for nuclear facilities. The second fundamental force of nature is electromagnetic. If you notice, it is roughly the same strength. It's only about 100 times weaker than the strong force. But one of the great things with the electromagnetic force is its range is kind of infinite. We use Coulomb's law for this. So the further you get away, the quicker it diminishes. But you could feel this at all different ranges. This can be felt in the macro scale of actually magnets that aren't even close to the atomic scale. But it could also be the one that's responsible for the proton attracting an electron in an atom. The next one is the weak force. This again the range is super short. So the weak and the strong force are both only found in the nucleus. We call this the weak force because this force isn't strong enough to hold the nucleus together. If you notice, this is much, much smaller than the strong force or even the electromagnetic. Because this force is so much smaller, it can't hold the nucleus together, and this is what is responsible for nuclear decay. The last force, which is massively weaker than all of the other three, is gravity. Just like the electromagnetic force, this can go for all different types of ranges. We've already spoken about how Coulomb's law looks just like the universal law of gravitation. They both have that constant. With gravitation, it's m1, m2 over r squared. For Coulomb's law, it's q1, q2 over r squared. Very similar looking force equations. So both of them will work over long, expansive distances, but the relative strength here is 10 to the negative 38. I don't even know what that number even is with 38 zeros at the end of it. So if you compare it to the electromagnetic, which is 10 to the minus 2, basically 100 times weaker than the strong force, or you get something 10 to the minus 13, which is still a lot weaker than the strong force. This is 10 to the negative 38 zeros. There's a huge gap in strength between the other three forces and gravitational force. So some examples will be asking how much stronger is one than the other. All we would do is basically count zeros. So we would just divide the two, and that would be it. Hope you enjoyed the lesson. Be safe.